So this electroscope thing, I stopped using the actual electroscope that looks like that because they break too easily. Sticky tape, you made one last week, and then we did the sticky tape lab, all right? And it's easy, it's cheap, and if you break it, we got another roll of tape. You know, it's not a big deal. And so the difference here being, the way an electroscope works is that plate that you see right here is connected to that rod, and then there's this leaf that's also connected to that rod. And so if you charge that plate either by conduction or induction, which those are the big topics today, then you will produce a electric force Coulomb effect, repulsion, or the lack thereof in this case. So this setup is no different than the sticky tape, except the way that you get the tape charged. That's all that's different. So with the sticky tape, you rip them off of each other and charges on both of them, and they repelled or they attracted. We saw that in our sticky tape lab. So now we're going to kind of thought experiment our way through a number of induction and conduction configurations to talk about the difference between charge distributions and net charge. And charge distributions is going to be its own monstrous topic soon enough, but now we'll get the basics going. So here you have this situation. You got situations A and B are the same with respect to the size of the effect. All right, in part A, you bring that positively charged rod near. Now here's the thing. We're going to talk about positive and negative charges, and then ultimately we're going to talk about moving charges when we get to circuits, which is one of the main events in the course. Positive charges don't move, as far as we're concerned at the moment. At least they don't move in matter. What would be wrong with positive charges moving in material? What's positively charged in matter? Protons. If protons start moving, we've got some serious problems. All right? Protons are stuck in the atom, in the nucleus, and they only come out by means of nuclear fission. Okay? You've got to destroy it. So as far as we're concerned, for regular, ordinary matter, which is what we're dealing with in an electroscope, positive charges aren't moving. But how many have had chemistry? Right? You know, obviously, the outer shell of pretty much everything on the periodic table, such as my shirt, which I wear periodically, which nobody can see on the video, but anyways. There's free electrons. Most things have some free electrons in them. Metals, in particular, have free electrons. That's what gets to move in material. And so if electrons move away from an atom, that atom becomes more positive. So think of the simple case, you got one proton, one electron. If you pull, that's a neutral charge. And most everything as it stands is neutrally charged. Essentially the entire universe is neutrally charged. All right? If you pull that electron off, now that atom has become positively charged. If you add an electron, it's become negatively charged. More electrons means more negatively charged. Less electrons means two things. Less negatively charged and ultimately positively charged. Or more positive in one sense. So there's those distinctions. All right, so back to the thing you're looking at. The difference between A and B is the magnitude of the effect. All right? Same thing is true with C and D. It's the magnitude of the effect. Now we need to talk about what's happening in both cases. When, situation A, if I bring a positive electric field near to a conductor, something that has free electrons, one, I already answered the question, which charges move? The electrons, the negatives. And our electron's going to try to move towards the positive rod or away from it? Towards it, because unlike charges attract. So every free electron in the electroscope, down inside the electroscope and on the plate that's nearest the rod, all of those free electrons are doing their best to get to the plate. It's a white sale at Macy's. Or first showing of, the next Avengers thing. It's everybody and their dog wants to get where the entrance point is. Okay? So a whole bunch of negative charges move, from down below to up here. There's all these negative charges that move up to that plate. And if that's true, it exposes a bunch of positive atomic cores. So the bottom of the electroscope became more positive. The top of the electroscope became more negative. But what happened to the net charge? Initially, it was uncharged. Uncharged doesn't mean no charge. Why doesn't think of the structure of matter. Why doesn't uncharged mean no charge at all? What's the one elementary particle that has no charge? What? Neutron?
Photon.
It's not an elementary particle. Protons, electrons, neutrons. Protons are positive, electrons are negative. Neutrons are no charge. So how much material is made purely of neutrons? None. Okay? There's no matter, nothing on the periodic table that's just neutrons. Okay? So the uncharged means the net charge is zero. Has as much positive as it has negative. The other lingo for that is neutral. Neutral, uncharged mean the same thing. It doesn't mean that there's no charge. It means that the net is zero. That's a subtlety that's not perfectly clear unless you do some reading or listening to somebody who says stuff. Okay? So that's one note to take, because these things are excellent ideas for your journals and essays. All right. Let's look at C and D. Same interaction, different magnitude of effect. If I bring a negative electric field near that plate, then what happens is the negatives want to get away. So they go as far away as they can from the plate, and that subsequently causes the plate to be positively charged. The mistake that people tend to make in this case, though, is they think that positive charges moved. Positive charges do not move unless you have a proton gun. If you can make a proton beam, then you have positive charges moving. Okay? Proton guns are not found easily or made easily, all right? And you don't find proton guns in matter. So if we're talking about a conductor or an insulator, protons are not moving. Positive charges are not moving. Those of you that will be electrical engineers someday, you will talk as though positive charges move in semiconductors, but protons don't move in material unless you don't have material anymore. You're melting it, all right, something like that. So plus charge causes negatives to come near it, minus charges causes negatives to go away. In both cases, you get the same effect of deflecting of the leaf in the electroscope, just like you saw and felt with the sticky tape experiment. No difference, just a different way to pull it off. All right, so we've talked this one out pretty much as far as it can go. So the nature of these questions, as you recall from last semester, is it's very easy to miss a subtle detail and be totally wrong, okay, because you missed that detail. So rank the net charge on the electroscope while the charge is near. So what do we mean by net charge? So if I have a net effect, it's a this plus a that, add it all up and I get a net, right? So did the total amount of charge change in any of these situations? Did the amount of charge change, or did the distribution of charge change? Just the distribution. And the reason why it was just a distribution of charge is that there was no conduction. Had that rod touched the plate, then there would have been charge transfer, and the net charge would thus change, because you would have a plus or a minus of something. Okay, you'd either obtain more negative or lose negatives, depending on the interaction. So, though the charge distribution inside of the electroscope changed, there was no charge transfer. So if the total amount of charge is the same before and after, how do I rank the net charge? Initially, the scope is uncharged, meaning it's neutral, just as many minuses as there are plus. Did the net charge change? Yes or no? No. So it looks like they're all the same. Okay? Or all zero, rather, not the same. And so there's a one-sentence version, and I had a paragraph-length version in my explanation. All right, so how you log that in your notes. It is true, the net charge on the electroscope, assuming the rod doesn't touch it, is 0 in all 4 cases, since no charge is transferred. So we're going to deal with induction, we're going to deal with conduction, and we're going to deal with both. This is induction, induced charge. If we had taken some of that sticky tape from our sticky tape experiment and brought it near something else, then that electric field could do induced charge things like this. But we didn't do that in the experiment because that wasn't our goal. Okay? Any questions on this one? All right. Oops. All right. This one is going to be a conduction. Transfer of charge in conductors. We're actually talking about charges moving from one thing to another. So in each one of these situations, A, B, C, D, this conducting spheres are identical in shape and composition. All right? Same surface area. Surface area is a big deal in charge transfer. More surface area, more charge capacity, so to speak. So in each case, those spheres are brought in contact with one another. And the goal here is to rank the charge on the left sphere from the highest positive to the lowest negative after they've been separated. So well, first, what is going to happen when these spheres touch one another? Besides charge transfer. What else about that charge transfer? If I drag my feet on the carpet and come over and touch you, what's going to happen? I'm going to transfer charge to you. So if one charge carrier touches another charge carrier, there's going to be charge transfer in one direction. From what to what? So in part A, which sphere is going to give up charge? What's that? Well, what's that? +6. One of them is going to give up charge. But what's going to happen to the total amount of charge on each sphere? They'll average out. So one way you could rank these is to compute the average charge. Because the left sphere is going to have the same charge as the right sphere after conduction. Because they're identical. The surface area is the same. So they will equalize charge, which can be computed by the average. So yes, the average is the most effective computational way to do this, but it doesn't give you one hint as to why. Okay? So if you add up the total and divide by the number of parts that are possible, that is an average. And it will be the correct answer. It is the way it will work out. So the ranking, so what's the average of A? +4. The average of B is -2. The average of C is -4. And the average of D is 3. So you have your ranking. A, D, B, C. That right there that I highlight is the only reason that charge works out as the average. If they were different sizes, it wouldn't be an average. Because the larger sphere would have more area, more space in which electrons could go. And that's where they will go. Electrons will always seek the path of least resistance, and the path of least resistance comes in at least two forms. One, the resistance of that material is less than something else. Okay? And there's literally more space for that charge distribution to fill up. Because electrons want to get as far away from one another as they possibly can. And so if we only had this many students in the room, we could all stick our arms out and get as far away from one another as that allows. If we doubled the number of students in the room, then we'd go to elbows. And if we triple, then it's going to be something else. And pretty soon you have a max capacity of how many students can fit in this room if we all stand like sardines. And I guess we could get on each other's shoulders, or we could stack it up that way, get more, and that way somebody's going to die though on the bottom. So that would be bad. I don't recommend that. Right? But there's a limit. They can only cram so many grams, so to speak. All right? They can't have an infinite amount of charge on a finite amount of space. Can't have an infinite amount of anything on a finite amount of space. So that's the main reason, because they're identical size and shape for that matter. Interestingly, sharp corners are a larger charge density than smooth ones in this land. So, all right. Any questions on that? All right. This situation, same ideas as before, except the symmetry brings us into oh, I have to hand that out to you, I guess. So in each situation, so let's look at the outer situations, the AB and the EF configuration, because they only differ in source field, okay, plus or minus. So in the AB configuration, a positively charged rod will be brought near, so that we're talking about induction, not conduction, okay? And so that means that electrons that are on B will do their best to get as far on into the A sphere as they can. So whatever negative charges are, and technically A and B are touching, so they're like one big sphere. Okay? Effectively, any two conductors that are touching are like one conductor. Okay? And so, because electrons know if there's room on the other side, and they will go. All right? So that means all of the electrons that are free to move on both A and B are trying to cram their way over to the left side of the A sphere. And if they could all pile up on the left side, they would. If there's room, they'll get there. So we can predict, generally speaking, that negative charges are going to be piling up here. And if negative charges pile up there, that means that this thing is becoming more positive. So the right-hand side of B will be more positive than the left-hand side of B, which will be more positive than the right-hand side of A. Did you catch that? The drawing's kind of small. Okay? So let me kind of redo that. So all them negative charges, they kind of want to get over to the right side of A. That means that they want to, if they leave the right-hand side of B, they expose that many positive cores, because every nucleus is positive. Got protons in it, okay? So it's sort of like, you know that the electron cloud model, okay, so I'm going to pretend that you've heard of the Bohr model that has like individual electrons in orbit. We know it's not that way. That's just an effective way to model it. Okay, it's part of the computations of it, but in reality it's just this kind of diffuse cloud of particles that pop into and out of existence. That's one oversimplification of it. So any atom is going to be more or less cloudy than the next one. So if I remove the electron cloud from an atom, I would just see a positive core. So the four, let's say that there were four on the right-hand side of B and they moved over to A somewhere. That would mean it would expose that right-hand side. But B, the farther I am away from the positive inducing rod, the more positive that part of the conductor will be. But there's going to be a pileup. So, there's going to be less negatives on the left-hand side of A than are on the right-hand, on the right-hand side of A than on the left. Okay? And that means that the left-hand side of B will be kind of positive and negative. And the right-hand side of A would be kind of positive and negative. See, before I drew anything, they were neutral. I bring in a positive electric field, and now the closer you are to the positive field, the more negative it is. The farther you are from that positive field, the more positive it is, and that's what I've drawn. Okay? I would suspect, though, that I would need B to be more positive than A. So I've actually listed it. It's 4 negatives to the most left of A, 3 on the right of A, 2 on the left-hand side of B, and then the opposite. Far side of B is as positive as the near side of A, etc. 4, 3, 2 in both cases. Okay? So you would expect a charge distribution to go like that, generally speaking. Okay? Generally speaking, it would be that way. And so over here on this one, the opposite would be true. I would expect, because of, and I'm going to do it in a particular order, this negatively charged rod brought near to E will cause negative charges on E to go away from E, go away from the rod. So when negative charges go as far away as they can from the rod, if I end up pushing 4 negatives to the far side of F, that means there would have to be 4 exposed cores. Not 4 positive moving charges, but the negatives that went over to the far side of F, they used to be on the near side of E. Now I just made up 4 arbitrarily. Okay, I'm just making that number up because it's an easy number to draw. Okay? Obviously there are millions of charges on material. And so if that's the case, I would also expect that maybe a little bit less negative charge would be on the other side of F, which means correspondingly there'd be that. But there's still some negative charge here, and there's still some positive charge there. It's not likely that you would totally make one all negative and the other positive. It's possible. That would be the most you could expect, is that F becomes totally negative and E becomes totally positive. I mean, it's certainly possible, but that wouldn't be very illustrative about the way that a charge distribution changes because of induction. All right? So again, induction doesn't change net charge. Only conduction changes net charge. Induction changes charge distribution. So those are 2 money lines right there that you could be asked to repeat in the future. Now, one of the reasons, well, the reason that you had an unequal charge distribution in those other 2 examples is symmetry. The line of symmetry did not allow for charge to equalize. It absolutely demanded that there be more of this on one sphere and less of that on the other. But in this case, these 2 balls C and D, they're like one ball because they're in electrical contact, they're conducting one another. Conducting spheres that are conducting to one another, and right now their charge is equalized. They have the same, the total charge is split perfectly. So if I bring a positive rod near, now I'm going to have a pileup of negatives as close as they can get to that rod, which means positives. So really all we're doing now is kind of skewing the charge distribution. The positives want to get as far away from one another as they can, so they do, but now it's along an angle instead of a straight line, so to speak. But because the line of symmetry, okay, no charge is going to transfer. So the thing to think about is what would happen if after this rod was brought near in each situation, if I separated the conducting spheres. Because if I separate the conducting spheres, leave the rod there, somebody pulls those spheres apart, those spheres will now have different charges. Initially they were equal charge, 0. Net charge is 0. But if I separate them after the induction, that changed the charge distribution, not the net charge for the two spheres, but the charge distribution. Now I'd have 1 plus 1 minus. So in the left and right hand sides, the AB and the EF conditions, if I were to separate those spheres, now they have different charges, different net charges individually. But in the CD thing, if I separate them, they will be identical. They will still be net charge of 0, which is what I've shown. In the other one, it was necessarily a net positive or negative. Here, it's still 0 because of the symmetry. All right? So, rank the net charge on each sphere from most positive to most negative after the spheres have been separated. So, which spheres are the most positive? B and E would be identical, we would assume, which means A and F would be the most negative, and C and D would be neutral. So you have, I gotta get this centered. So this narrative says pretty much what I said. Charges want to move away from the rod that's identically charged. Well, negatives either want to move towards the rod or away from it. That is clear. It's so easy to say the positive charge is moved because you're forgetting that that can't happen in material. So that's one of the biggest hang-ups with this business. So correct, B and E are going to be identical. C and D are going to be identical, and A and F. And obviously plus, 0, minus. That's why they get in that rank order. So, writing these, greatest BE, CD, AF, if you were going to fill in the blanks. Any questions on that? Yes.
So on the middle image, if you took like both of them below the line of symmetry and then separated them there, they would have unequal charges?
Correct.
All right.
Yeah, so symmetry is what makes it neutral for CD. And it's because any other configuration is going to be unequal. So now we haven't talked about grounding at all. So let me explain a thing or two. So also, we haven't talked about insulators yet. So if you did the reading, inevitably you would have noticed, or maybe you will recall when I repeat it, insulators don't conduct charge, but they can hold a charge. So an insulator is a weird surface in that you could have some charges pile up in one region of the insulator, but they will never distribute themselves equally on that insulator. And they don't transfer charge readily. Okay? So an insulator is basically something that can produce an electric field, but it won't transfer charge. Okay? So, bottom line, insulators don't transfer charge even though they can hold charge. You can transfer charge to an insulator, but it's hard to discharge them. It's not impossible, just the way they work. Now, a conductor will absolutely transfer charge if it's in contact with a charge source and it's not at its maximum capacity to hold charge. This conductor, that little squiggle line off to the right of it, is a grounding line. That's how we would indicate a grounded circuit if we were doing circuit analysis. So, you can look at the wall next to you and you'll see a plug in the wall that has a ground socket. So the idea of grounding is that you want to provide a path of least resistance. So for instance, if the stream of electrons has a choice of going through your body, which is millions of times more resistant than, say, a metal wire, it's going to choose the metal wire because they're lazy. Okay? They don't want to do much work. And so that's why we ground things, so that there's this nice, beautiful path for trons to go their merry way and not mess up yours. Okay? So this conductor, that means if it's connected to ground, and ground can be anything. The ground can literally be the ground you're standing on outside. It could be the table. It could be a metal plate on the table. A grounding plane can be anything that charge can move to or from. Okay? And so ground doesn't necessarily mean dirt. It just means some sort of material that charge can move to and from. Okay? Ideally, two. That's the whole idea from a circuit perspective, is a path for, it's like a ditch. Ditches prevent flooding because it's a place where water will flow more readily than a flat surface. All right, so that's the same basic idea as a ditch. All right. So in this situation, we're going to, what if anything's wrong with this statement that some student makes? When the charged insulator is brought close to the grounded conductor, okay, it will cause the negative charges in the conductor to move to the side closest to the insulator. True or false? Will a positive electric field cause electrons to move toward it? Yes. Free electrons will move towards a positive field. Period. They will move upstream in the field because an electric field coming from positive is going out from the source. Electrons want to go upstream. They want to go, they're attracted to it. Whereas positive charges would want to get away from it. All right? If they could. All right, so that's true. Yay. If the charged insulator is taken away, the conductor will be left with a negative charge evenly distributed over its surface. True or false? 50-50 chance.
False.
The false is the correct answer, but why is false the correct answer?
It wouldn't be distributed around its entire surface. It would be where the insulator was.
No, nothing will go to the insulator they didn't touch. So the fact that it's connected to ground, that's why it'll just go back to ground. Because in addition to pulling free electrons that were on the conductor surface, it pulled electrons from ground. So you literally, in this case, you have negative charges, more of them going here than here, but they are being pulled from ground. So you can pull charge from ground. All right? And so if that insulator is taken away, thus taking away the positive electric field that caused the draw of charge, well then all this just goes right back. And it would go back to being neutral. All right, so the answer is that last statement is a problem. So the conductor will go right back to the way it was before the thing was brought near. Now, if there were no grounding wire, or if you cut the ground wire before you move this inductor away, or the insulator away, then yes, you would have a change in net charge. So while the insulator's there, we increase the net negative charge on the conductor because we pulled him from a place other than the conductor. And the only way that we could increase the charge on the conductor would be to cut the ground wire before we move the insulator away. But if we don't, it'll just go right back to the way it was. In this situation, we now have a size differential that will change things a bit. So spheres A and B, where B is smaller than A, initially uncharged and touching, so they are at an equilibrium of some sort. And if they're uncharged, they both have the same net charge, even though there might be more charge on one than the other. A third conducting sphere is positively charged, meaning it has a deficiency of electrons. That idea is the key idea. It doesn't mean it has more positive charges on it. It means that it has a deficiency of electrons. Okay? A less electron cloud means more positive because you're exposing those spheres. In fact, I think in one of the lectures online, I had a nice image that showed that more explicitly, if I remember right. All right, so this first question, the answer is given already. Is the net charge on sphere A at this time positive, negative, or zero? And so if you bring a positively charged sphere near, that means a bunch of negatives want to come over here, which means a bunch of positives are exposed over here. So the deficiency of electrons that are caused from some number moving from A to B means that sphere A is positive. It's a net positive at this point. And if we were to separate them at this point, A would be positive and B would be negative. And it would stay that way. But if we move sphere C out of the way, then it just goes back to neutral. Right? And then part B is the inevitable opposite answer. Okay? If one got more positive, the other had to get more negative. So kind of a no-brainer on those two. So now, if we come down to C here, is the magnitude of the net charge on sphere A greater than, less than, or equal to the magnitude of the net charge on sphere B? So magnitude. We've already determined that one's plus and one's minus, but do they have the same magnitude of charge? Absolute value, if you will. So think about what must be true about any charge transfer due to conduction. If 10 electrons leave one conductor and move to another, that means that original conductor has a -10 deficiency of electrons. And a -10 deficiency means that there's 10 more cores that are visible, so to speak, if you're trying to look at it visually. So if 10 electrons move away, wherever they go to becomes 10 more negative. And wherever they left becomes 10 more positive. So literally think of it as you know, if you have a positive core, all right, well, this electron pretty much blocks it out. All right? And you see the negative. But if that electron goes away, then you just see that positive core. So an electron deficiency has a necessary result of a positive surplus. Okay? So, because one negative and one positive is a net zero. Pull away the negative, you got a +1. On the other side, where the electrons move to, they move to a place where there were a bunch of +1s and -1s. But if I throw an extra -1 on it, now this one is a -1. Because a +1 and a -1 and a -1 is -1. Right? +1 -2 is a -1. So it has to be equal and opposite. Conservation of charge, if you will. Okay? Has to be equal to. And the simple answer would be for each electron that moved from A to B, a positive was left behind on A. All right? And I labor this point because it's so easy, people will still mess it up for a while after this. An electron deficiency is an exposed atomic, a more exposed positive core, atomic core. Because the positive atomic cores are not moving. They're certainly not, they're getting stretched, but they're not moving out of that place. Yes?
So, my intuition would say that you would take the whole diameter of sphere A plus B, cut it in half. Anything like further away from sphere C on that half would be a positive net charge. Anything closer would be a negative net charge. So like it would be like sphere A would end up having little like a part that like has a net negative charge in that case. But like
The best that you could hope for, well, it's yes and no. I wouldn't just limit yourself to that. It's possible that all the electrons could leave a sphere and go to the other one. It's possible that it could be half and half. It's not necessary. Neither one of those is necessary. It depends on the size and the charge. What I'm showing is the general effect. Generally speaking, the farthest away will become the most positive or negative depending on what's inducing that charge transfer. So I would leave it in those general terms. But just you can't just say it's always split the diameter in half and da-da-da. So just I would go with the general effect of you bring a positive field near, the farthest point away in the conducting loop will be the most positive.
I was thinking in terms of sphere C, not A and B, say.
I'm not sure.
Like my question was like thinking I was asking about A and C, but I was asking about A and B, so that's why I was confused.
Okay. Yeah, I might have to tackle. I'm not sure that I understood you fully, but I wouldn't try to put a formula to this. This is not something that can be pinned down quantitatively. This is a qualitative discussion. So trying to put any sort of numbers or partitions on it is not going to work for us. All right. All right. Let's just do the reveal on that. So this one, now we have moved, instead of the initial condition where sphere A and B are touching and neutrally charged. Sphere C is still the same way it was before, except now we're just going to move sphere B over to it and touch it. All right. So last I checked, sphere C was initially positive. Okay. And if sphere B comes in contact with sphere C, what will that do to sphere A? To the net charge on sphere A. Again, which process can change net charge? Which one?
Conduction.
Conduction. Did A experience a conduction event by moving B over to C? No. If A had eyes, A could watch a conduction event between two other spheres. Okay? So sphere A did not experience a conduction interaction. Therefore, its net charge did not change. The only way that you can change the net charge, the total amount of charge on an object, is through conduction. There has to be a way for charge to go from one place to another, either increasing or decreasing the net charge somewhere. Induction just moves them around where they're at. So for instance, if I made everybody get up and switch tables, the net number of students has not changed. Your distribution has changed, but it's still the total number of students in the class. Now, if I invite another class, or start kicking people out, then that would be like a conduction event. There was a way for you to get out. Okay? So, these exercises, all but the last sheet that we're going to do, which is a few away, I think, are about the difference between conduction and induction and the permutations therein. If you do it in this order, can you change the net charge? So you could have an induction event followed by a conduction event that leads to a change in net charge. But no series of induction events could ever alone change the net charge. They would change the distribution of charge. So knowing that induction changes charge distribution, but conduction changes net charge, those are the fundamentals. Those would be the bottom lines, so to speak, for everything we've seen so far. And then this last one. Does the magnitude of the net charge on sphere C increase, decrease, or remain the same? Well, sphere B was neutrally charged, meaning it has just as many negative charge carriers as it had positive, one electron per proton, if you will. Okay? It's like Noah's Ark. Just pair them up, all right? So that means that there's free electrons. And if you put something that has one or more electrons in contact with something that's positively charged, one or more electrons are going to move onto the thing that's positively charged, because those electrons badly want to hook up with a proton. Okay? So, absolutely guaranteed that sphere C must become less positive, because it's going to, coming in contact with a neutrally charged or negatively charged source, conduction absolutely will begin to fix the electron deficiency of the positively charged thing. That's another thing to get in your mind. Net positive charge means electron deficiency. Period. Net negative charge means electron surplus. Neutral or uncharged means just as much positive as you have negative. Equilibrium. Doesn't mean zero charge, doesn't mean nothing. So that's one of the things about physics is we have about 8 versions of nothing. And none of them are absolutely nothing. They're all different ways to express. I got just as many of the ups as I have downs, lefts as I have rights, etc. All right? And so charge conservation is fundamentally linked to energy conservation because charge carriers, it's a way to transfer energy, loosely speaking. Okay? So, any questions on that? Yes?
So would the lower net positive charge on C be by means of conduction?
Yes. Electrons are going to, let me draw this since I can. So in this case, electrons are going, so what'll happen is some number of electrons will come over here. And so let's say those two are going to pair up, thus reducing the net positive charge. It's a good question because it lets me draw. But because those two negatives left sphere B has an electron deficiency and is necessarily more positive than it was, to the exactly opposite to the less positive that sphere C obtains. So that if you can get in your mind that only the negatives move, positive charge means electron deficiency, negative charge means electron surplus. Okay? And so anytime you pair up a plus and a minus, you've just reduced the charge quotient, if you will. Okay? But you can only move negatives over to where positives are. You can't move positives to where negatives are. So getting that in your mind that it's always a game about where did the negatives go. And those have equal and opposite results. Wherever the negatives go become more negative, which is the same as less positive. Okay, so that's why this one, it lowers the net positive charge on C because negatives went and canceled out. They went and clouded some of those positive cores. That would be the most up-to-date viewpoint. And it's a cute metaphor. You know, this atom is more or less cloudy than the next atom. Its electron shell, or electron shells, the layers in its atmosphere, if you want to really take the metaphor all the way. You know, so something like hydrogen has one cloud layer. You know, every other element on the periodic chart has more cloud layers. They got some shells pretty deep and wide. You know, 26 electrons in the shells and 7 shells, and you know, it's all spread out. That's a really cloudy atomic core. And if you take all the electrons away, you have no clouds. And that's as positive as it could get. A proton. All right, so hydrogen is as thin as the clouds could be if there are clouds. One electron. All right, so If you've had chemistry, then that structure or matter thing will ring a bell. If you haven't, it'll be harder. All right, let's unpack this puppy. So now, an insulating rod. So remember, insulators can hold the charge, but they don't transfer it. So an insulator can actually be an electric field producer. An electric field producer. Is more better grammar. All right. Then a neutral conducting sphere. Flat earthers have nothing to fear but sphere itself. Get it? You know how we know the earth can't be flat? I mean, there's some physics reasons, but there's a more simple reason than any of that. If the earth were truly flat, cats would have pushed everything off by now. Since we still have stuff, and we have cats, the earth obviously isn't flat, so. All right, student is either right or wrong in this case, so we'll find out. So we're going to take this sentence by sentence. As the negatively charged rod nears the sphere, it causes the electrons in the sphere to move far away from the rod. Okay, so here's this negatively charged rod. And so that means that negatives will, in fact, want to get away from that rod. If that's the case, then you will correspondingly expose positive cores. Hopefully that's not controversial. Now, the side of the sphere nearest the rod becomes positively charged, while the other side becomes negatively charged. That is what I just drew. That seems undeniably true, unless everything is a lie in your physics textbook, and I am a peddler of lies, okay? I sleep well at night, so I don't think I'm a peddler of lies. And this idea has been pretty solid for a while, so I'm pretty sure that nobody's lying in the textbooks. All right. If that's true, isn't it the case? If you got a bunch of plus things close to a bunch of minus things, there's attraction. Now that seems like, well, wait a minute. I thought it pushed the negatives away. Well, yeah, in pushing them away, it opened up all these positives, and poof, there's attraction. Okay, so you might be initially, if we could like slow-mo video it, it might initially push it away if we could catch that moment. But more likely not. I don't think that would show up. But I could be wrong. Been wrong before. So the sphere will be attracted toward the rod. I agree with that. Then, so far, I think that everything's legit. Then this last statement, if they touch, the sphere will swing back since they will both become neutral. Either that's correct or it's not correct.
It's not,
Why is it not correct?
because the insulator won't lose its strength.
Because I said so. All right? But yes. So, first three sentences are correct, but the rod cannot become neutral because it's an insulator. And so there's that raw fact that you could memorize and repeat without understanding. So more deeply, like I said before, an insulator can hold a charge, and the reason for that is that irregularities in its surface allow for excess charge, negative excess charge to be there. But it can't equalize charge on its surface. Okay? You could conceivably get those negatives off, but it can't equalize charge on its surface. All right? So it falls apart because, now if it were a conducting rod, yes. If it were just a metal rod, you bet we could get neutrality, but not with an insulating rod. All right. Pretend you didn't see who was correct. Just getting the right answer is it? Because here's the thing. Another reason we do this, it's a double duty here, because I put these on the test too. So these things are ideal for your journal and learning outcome essays. They're great stuff. Source material that you've already worked out. And I'm going to give you some more of these on your test. So the proficiency helps. All right, so I guess, I don't know, aren't these people like from Romeo and Juliet or something, Amadeo, or something like that? So, some old play. So let's see what Amadeo has to say. There are positive charges that jump from the rod. Okay, no. We can write him off right off the boat, right off the bat. So again, it's electroscope, charge rod brought near, and we saw this in the very first example. That means electrons want to move to the plate, leaving positive course exposed on the electroscope. So you get the deflection that you see. But positive charges, not only do they not move, but they're certainly not going to jump. Okay? And the electrons wouldn't jump unless you had so much charge that it was a lightning bolt effect. Okay? But it takes an enormous amount of voltage to break down air. So that's why lightning takes, Mother Nature's help. Okay? She's kind of buff, so to speak. She can get a humongous potential difference between the ground and a cloud and then break down the air. And that's what when you see a spark, that's what it's broken down. The voltage difference was high enough to break down the air in that region. So the smaller the gap, the easier it is. All right? But guaranteed, there's no way to put enough charge on an electroscope so that a spark would form. And if it was, it'd be a minus jump, not the other way around. So we write Amadeo off right off the bat because what he's just suggested is impossible in matter. All right? Baroon. Charges don't have to move from the rod to the plate to deflect. That is correct. When the rod comes close, electrons in the electroscope move toward the plate. Correct. We already worked that out in a previous exercise. This leaves the bottom of the electroscope positively charged. Correct, because it has a deficiency of electrons, which means exposed positive course. And the leaf lifts because they're same charge. Like charges repel. So at this point, we would say, well, I guess Baroon got it right. And usually there's not two correct answers on these, but let's take a look at Carmen. Positive charges are fixed in place. Correct. When the rod is brought close to this plate, the electrons in the plate are attracted and jump to the rod. No. So it's determining, when does this statement fail? Okay? And it's natural to hope that an electron could move all the way to where the proton is. Okay? Seems why not? Well, it just doesn't work that way in nature. So one of the things about science does not often deliver common sense results. Rarely does science deliver to you common sense results. It delivers the unexpected quite frequently. It's not as simple as we'd like it to be. All right? Now, for some folks who become very proficient in science, it might feel like common sense, but that's a mistake. It just means that it's easy for you because you have a broad base of knowledge and a lot of experience. That doesn't mean common sense. So, anyways, any questions? So Baroon gets the winner, winner, chicken dinner prize. And basically everything that I said is repeated in a slightly different way in that narrative. And you could always go to the video later once it's posted and watch that. So any questions on that? All makes sense. It's really kind of cumulative as we move through these activities. All right, so we'll just start with the right answer and move on from there. So same situation, positive rod near the top plate of an electroscope. This would be no different than bringing one piece of tape near to another piece of tape. Going back to our sticky tape experiment. In fact, you could perhaps take any one of these sheets or any number of them and simply compare them to the results of your sticky tape lab, and that's a great journal entry, learning how to become essay entry, etc., etc. Meanwhile, back at the wrench. Is the electroscope now positive, negative, or neutral? Well, it's still neutral for a number of reasons. That's what it says on the screen. Okay, but charge distributions don't change net charge. That's that you're driving that concept home in. That the total charge on the electroscope didn't change just because everything moved around. The charge on the inside of the electroscope is different because of the distribution. I have an electron deficiency inside where the leaf is, meaning I get the effect of like charges repelling, but I did not change the net charge. Therefore, the charge on the electroscope is still neutral. The electroscope as a whole thing. So the short answer here is, you could say, don't confuse the distribution of charge on the plate relative to the distribution of charge on the leaf as meaning that the total charge has changed. The total charge has changed in those subsections of the electroscope. That's not the same as the charge changing. So charge distributions don't change total charge, net charge. It's that simple. I guess the other thing, if you change the charge, you have to conduct. There has to be a charge transfer to change charge. So if you can't detect a charge transfer, you don't even need to understand the charge distribution. If it didn't transfer, if it didn't conduct, charge is not changed.
So is this inducting?
Yes, this is induction. Induction is failing to conduct. But induction still exerts a force based on the Coulomb law distance. Okay? So, I'm gonna give away this one before we get to the last one on this page, or last two, whatever they are. So, now here's the difference. Same situation as part A, except person touches the plate and the leaf appears to discharge. So, before the finger touched the plate, positive, net positive on the leaf and rod meant deflection. You touch the plate and the deflection's gone. There's only one way that that can happen. Negative charge went from person to electroscope and fixed the electron deficiency that caused the leaf to separate from the rod. So, net positive on the leaf and rod was because of the electron deficiency caused by the positive rod about near the plate. Touching the plate resulted in the effect of the leaf and rod no longer deflecting, there's only one way to do that. Fix the electron deficiency by adding electrons to the system that were not there before. Okay? So now the electroscope as a whole, instead of being neutrally charged in spite of a charge distribution that led to an effect, now it truly is negatively charged because negative charges got added to the system and that ended the electron deficiency that caused the deflection. So having that sequence of facts in your head explains this phenomenon and preserves all of the underlying concepts therein. Any questions on that? So you just got to think about the observed effect would be that the deflection goes away. And the only way that could be true is if a formerly positive repelling thing stopped being positive. Now, had it been switched to being a negative, fully negative, both negative, then it would repel again, but it didn't do that. The effect was the leaf stopped repelling. It went from being positive to not. So it equalized. It got to a neutral standpoint. Now, there's a reason for that. That positive rod above the plate is still pulling electrons up. And there's only so many electrons that could be transferred to the electroscope in the first place. It has a limited capacity to store charge. All right? Any questions on that part, part B? Now part C, while holding the positively charged rod stationary, she removes her hand, which is touching the electroscope. Now, we already have the answer to this. If before she removes her hand, the overall charge on the electroscope is negative, what's going to happen when she removes her hand? It's going to stay that way because of conduction. The hand conducted electrons to the electroscope, producing an observed effect of ending the deflection on the leaf and rod because it fixed the electron deficiency that caused it in the first place. Charge was added. It was transferred to the system. And if it was negative charge transferred to the system, that means it's negatively charged now. It's not like as soon as she moves her hand, they magically jump back to her hand. There's no reason to think that. She added charge, then she removed the source of that added charge. That charge stays. So the answer, which we basically obtained from the prior stage of the question, is that it is negatively charged. So it's still the overall charge on the electroscope is now negative. It's still probably pulling more up to the plate than are down low. But it's probably maxed out its capacity at this point. So part D asks, so part C says, so then she removes the rod. Okay, so think of it, positive rod brought near, electron deficiency inside, leaves separate from rod. Finger touches plate, leaf falls because the electron deficiency was cured. Hand is removed, and the electroscope is negatively charged, just like it was before the hand was removed. But that positive rod is still drawing electrons to the plate. Remove, so what you would have is an unequal charge distribution. More negatives at the top than the bottom. You remove the rod, what's going to happen? Everything's going to settle out. Because now all the electrons, they got nowhere to go but plate and rod and leaf. So that means they're all going to get as far away from one another as they can, just like if we put our arms out in this room, we all could occupy almost same size space. And so those electrons are like, back up, bro, personal space. Okay? Electrons are very particular about that. And so they would just spread out and basically be equidistant from one another. The only difference would be if there are any sharp edges, then they'll pile up near the sharp edges. Okay? That's an interesting phenomenon that we'll get to later. And so if that's the case, if you have a negatively charged electroscope, that means the rod and the leaf are negatively charged, correct? And if they are the same charge, what's going to happen to the leaf and rod? Will they separate or not? They'll separate because they're the same, like charges. Except it went from a condition of positive electron deficiency, if you will, causing the separation, to an electron surplus. Same effect, different cause. All right? So this situation takes us all the way around the block. A neutral scope that obtains a deflection because of positive electric field drew electrons to the plate, thus producing a electron deficiency in the rod and leaf part of the system, and therefore a lifting of the leaf. Conducting free electrons from a person to the plate fixed that electron deficiency, removing the separation between leaf and rod. Removing the hand did nothing to remove the charge that was added. So you have a negative scope, you pull the rod away, no longer drawing electrons to the plate, and charge distribution equalizes so that you have a uniform charge distribution, charge density everywhere, thus making the leaf and rod same charge, therefore repelled, and the leaf lifts back. So that's the long and short of that one. So now we're going to move to a Coulomb effect. Okay, so this will be our now we're going to actually use the Coulomb force law, and so hopefully you recall from the other day when we developed all this that the electric force is K Q1 product of charges over the distance squared, distance separation distance squared. And what that implies is you could say that force is proportional directly to the charge product and the square of distance. The constant isn't that helpful for us. So we'll look at the example and this first answer. So in the example that you could base all of your subsequent reasoning on, you have a charge separation of 4 blocks. And you have a force arrow that's 2 blocks long. And this is what you get when the charge magnitudes are 1. All right? That's the key idea, because ultimately the size of your force vector arrow is going to be contingent on the magnitude of the charge product and the distance, separation distance squared. So you have to kind of establish our baseline for what one charge unit and one distance unit is. So basically 4 squares is our 1, distance separation of 1. Okay? That's basically what we're defining here. So in part A, now the product of charge, instead of it being q squared, it's 2q squared. The q squared's irrelevant. We know it's going to be q squared. And we don't have a value for q. It's not important. I'm literally looking at what's the coefficient on q. Okay? And so the distance didn't change. But now the force interaction is twice as big because I have 2q squared instead of q squared. Hence the arrow, instead of being 2 blocks wide, is 4 blocks wide. Because 4 is the double of 2. All right? So we're sort of establishing the way we reason through these. So the next one, you have the situation where, okay, in part B, it's a minus 2q and a plus q. So what's going to happen to the direction of the arrows? Well, it has to go the other way. So if a plus and plus was going out oppositely, plus and minus has to go towards one another. So plus plus configurations and minus minus configurations go away from one another. All right? Because they repel. But if it's opposite charges, they have to go at each other because they attract. So there's the arithmetic of it, and then there's the vectorness of it. And arithmetics aren't vectors aren't arithmetic. Not even close, unless they're all along the same line. All right. So that means I have the same magnitude of charge product. It's a 2q squared. It just happens to be a minus 2q squared. Because I have a minus 2q times a plus 1q. That's a minus 2q squared. So I'm going to have the same arrows, except now they're facing each other, and follow the pattern of the left arrow is always on top and the right arrow, or the right charge, is always on bottom. That way you'll have a right view of it. Okay? So one way to think about, I'm going to go back to B. This force is due to that charge. And this force is due to that charge. And the combined, each force has to be equal and opposite, because that's the definition that we have up here. The product of charges over the distance squared. So they have to be pointing at each other in B because they're opposite charges. And the magnitude is still at 2. So relative to our original example, it has to be 4 squares wide instead of just 2, because I doubled the force size. Are we good to go? All right. The next one, part C, fundamentally, did anything change in part C? I have mathematically, computationally, I have the exact same ratio. The difference is now my plus charge is the 2 and my minus charge is the 1. But I still have a minus 2q squared. So I have the exact same force compilation. Absolutely identical. It doesn't matter which one's bigger. It's not that there's a bigger force on one than the other. Newton's third law. The forces on these two things are always equal and opposite. Either they're pushing away or they're pulling together. That means two different directions. One force magnitude. Okay, so this forces us down that path. All right, so that's part C. Part D. Okay, now things have changed. Now I have a magnitude in my force product of 4. They're still pointing at each other because they're opposite signs. So the signs here don't have anything to do with the magnitude of the force. They have to do with the direction. So now, if I have a +4 charge product, or the magnitude is 4. Well, if magnitude 1 in the example is 2 squares wide, what's a magnitude 4 force going to be? Because it's still the same distance as the example. 8. So the arrows are still going in the same directions as they were for the last 2 examples. But since the product of charge has a magnitude 4, the length of the vector arrows has to have 4 times the magnitude as our example, which was just magnitude 1. Or twice as much as the magnitude 2 examples, however you want to look at it. So the key idea here is so far we have not changed the distance, which means we haven't done anything to increase or decrease the force due to separation distance, which is an inverse square relationship. But we have changed the magnitude of the charge product. And if we make it a bigger magnitude, then it's a bigger magnitude. What a profound statement. All right. E. Now we've messed everything up. Now we just doubled the distance. What happens, what coefficient do you get in the denominator of the force law if you double distance? So think about when you say d squared, what you mean is if d goes from 1d to 2d, what number pops out of that doubling of distance? If d is 1, and then I double it, what happens to the 1 squared is 1. If I double 1, I get a, and if I square a 2, I get a, so now my force is going to be 4 times less for doubling the, 4 times less than my example, which is the distance 1 force, charge 1 magnitude example. It's your baseline. So that means that this have the same configuration as C, right? Isn't it a minus Q on left and a plus 2Q on right? So that means my answer for C has to be 1/4 of that. Because I have the same charge product, but now I'm cutting it to 1/4 of what it was. 1 box. And then this makes sense because what did we learn about the Coulomb law? The product, the force is directly proportional to the product of charges and inversely proportional to the square of the separation distance. So if I increase distance, I exponentially decrease the force magnitude. If I were to triple the distance, it'd be a 1/9. So it's not linear. It's a power function. Exponential in one sense, but not the letter E exponential. Then the last one is the same distribution as we had in D as far as charges go, but now double the distance. So I would take the situation in D and it has to be 4 times smaller, right? So that would be 2 blocks, which is identical force magnitude as the example. So at double the distance, double the charge gets you the same as magnitude 1 charge and magnitude 1 distance, the way we've defined it in this system. All right? So that's a wrap. There is a narrative that's provided here, but I'll let you read that on your own.